Hello, I'm going to be taking the time to explain basically all the answers to quiz 3 and the work that I did for them. So starting from number 1, note that these are going to be probably out of order because the order for everybody's quiz is different. So just pay attention to the problems themselves are. So my number 1 was uniform circular motion. An object moves with a constant speed of 30 meters per second on a circular track of a radius of 150 meters. What's the acceleration of the object? So this is pretty straightforward. The equation that we know for acceleration when it comes to circular motion is acceleration is equal to the velocity squared over the radius. So we know the velocity, we know the radius. All we do is plug them in, and we have our acceleration. For the second question I had was projectile motion. It's like a conceptual question. So for general projectile motion with no air resistance, the horizontal component of a projectile's acceleration will be, and the answer is always 0. So when you have a projectile, it's going to have the acceleration of the y component. Usually like on Earth, it's gravity or it's given to you. Like gravity on the moon, gravity on Mars, whatever. It's usually gravity. And acceleration with respect to gravity is always going to be negative gravity. Gravity itself is just the straight up like absolute value of whatever force that is, which is like going to be 9.81. Sorry, not force, the acceleration, which is going to be 9.81. But the acceleration on the vertical component is negative 9.81 because it's going down. There is no acceleration on the x portion because the velocity on the x portion is always constant when it comes to these problems. Therefore, there is no acceleration. So that's that one. So question 3 is a little bit of a doozy. So for mine, it was this projectile motion problem. So as shown in the figure, a heavy rock, let me erase that. A heavy rock is shot upward from the edge of a vertical cliff. It leaves the cliff with an initial velocity of 15 meters per second directed at 25 degrees from the vertical and experiences no appreciable air resistance as it travels. How high is the cliff? So it's asking you to solve for the height of the cliff. So the weird part of this problem is that it says 25 degrees from the vertical. So it's not as straightforward as we think it is. So from the vertical is actually this component up here. It's not from the x-axis, it's from the y-axis. So to make our lives easier, we are finding what it would be if it was on the x-axis over here. So 90 minus 25 is 65 degrees. So our theta is this one actually, is this one with 65 degrees. So we know our initial velocity is 15 meters per second. We know that our change in the x-axis is 3.4. And we know that our final y value, it's on the ground, so it's going to be 0. So our initial y is the height. So we basically have to find y initial. I believe it's, yeah, this problem. Okay. So first off, using trigonometry, we know that we can get the initial x component of velocity using the initial velocity cosine of theta and the initial y component of velocity with initial velocity sine theta. So solving it all the way through, we know that the initial velocity is 15. We know that the degree is 65. We can solve for Vox and Voy. Let me make my marker red. Okay. So knowing these, we can solve for t. So I know we just said we have to solve for height, but we can't do that unless we find the t first. So we can find t by plugging it into this equation of x. So we know the x final is going to be 3.4. x initial is 0 because it's just straight up the origin. We just solved for Vox, so we plug that in there. We just solved for, sorry, no. There is no acceleration of the x component. As we just mentioned, it's 0. So this entire section is 0. This part doesn't matter. So that's why this is 0 over here. So once we plug everything in, we find that the value of t is 0.536 seconds. And then now that we know t, we can find y initial. So we put in the exact same equation. So y final equals y initial plus the velocity of the initial, like y component, times t plus 1/2 the acceleration of the y component times t squared. So this is a pretty common equation that you're going to be using throughout this entire projectile process. So we know that the value of y final is 0 because it literally is on the ground. We're trying to find y0. We're solving for this one. So we have to be able to plug in for literally everything else. So we solved already for Voy. So that is this value over here. We know t because we solved it, so that's this value. The initial the acceleration on the y component is just gravity. So that's going to be, negative gravity. So that's going to be negative 9.81. And then the t, you put it again, plug it all the way through, you find the velocity, we find the placement of y initial. So yeah, that's pretty much it. For this next problem, uniform circular motion. Shown below are the velocity and acceleration factors for an object in several different kinds of motion. In which case is the object's velocity changing while its speed is not changing? So I only put one option here because it's the correct option. It's the first one just to save space, but it is this response. So, oh, sorry, I should note that for problem 3, the correct answer is like 68 or something, 68 meters, but that's wrong because 68 meters is if you had calculated it using 340 meters and you are given 3.40 meters. So I don't know what the problem with this problem is, but the correct answer is incorrect. I'm hesitant to say that it's a problem of the system, maybe something, whatever, but I know my math is right, so do with that what you will. Okay, so in uniform circular motion, we know that in circular motion, the vector velocity is always going to come out tangent to the surface of the circle, and that's why it comes out like, oops, sorry. I guess a better representation would be like using a straight line. So it kind of comes out like that, always tangent, you know? And the acceleration will always be perpendicular when it comes to circular velocity. Okay. Relative velocity. On a calm day with no wind, you can run a 1,500 meter race at a velocity of 4 meters per second. If you run the same race on a day where you have constant headwind that slows your speed by 2 meters per second, how much time is it going to take for you to finish the race? So this one's pretty easy too. So if you have like a starting point and you are this dot and you are traveling at a speed of 4 meters per second, the wind over here is going to be slowing you down for every 2 meters per second. So the wind is slowing you down. So you can solve for your total, your final velocity using this pretty simple equation, just algebra. 4 minus 2 is 2. So the sum of your velocity, the sum of your speed is going to be 2 meters per second. So in order to solve for the delta t of your total velocity, you know the delta x, you know the distance of the race, and you also know the velocity of the final your total velocity. So when you plug it in, you can solve for delta t, and that's just 750s. That's pretty easy. Okay, so projectile motion. A ball is thrown at an original speed of 8 meters per second at a height of 35 degrees above the horizontal. So thankfully, it's above the horizontal. If there is no air resistance, what is the speed of the ball when it returns to the same horizontal level? So let's take a look at this. So this is where stuff starts getting a little bit complicated. So we know that our initial velocity is 8 meters per second. We know that theta is going to be 35. And we have basically the 3 different points of projectile motion. So point A is the very beginning where t is 0. And point B is the peak of the projectile, is the highest point. And the highest point is always where the velocity of the y component is equal to 0. It's completely stopped at this point. And then we're trying to find actually the velocity at point C. What is the velocity going to be when it returns to the same horizontal level at the ground? So we use trigonometry to find the initial x and y components of velocity because we're given the angle and because we're given the initial velocity. Because we have these 2 values, we know to do this trigonometry thing. So given these 2 values of the initial velocity and of the angle, we can solve for Vox and Voy, Vox and Voy, which is 6.6 and 4.6. So first, before we can solve for the final velocity, we have to find t first, which is pretty simple. So we don't have to mess with the velocity of Vox to find t because it's constant, because we know that acceleration on the horizontal is always 0. So we're not going to have to mess with that. What we're going to mess with is the y component. So we know the value of Voy, and we know the value of acceleration of y, and we can plug in for what the velocity would be at the highest point. So Vy at the highest point is equal to 0. And it's also important to note that the t that we're solving for in this step, if you look at it, this is this section of the problem that we're solving for. So this is only halfway through, right? So this is like delta t of A to B. This is only halfway through. We need the full length because we need to find VF at point C. So at the end of this current equation that we're going to do, we're going to have to multiply by 2. But one step at a time, right? So at the highest point, Vy is equal to 0. So you plug in your Vy over here. You plug in the V0y that you calculated. You plug in gravity, and you solve for t. So the t from A to B is 0.47 seconds, and t from A to C is the same thing but times 2. So it's the full length of the parabola. And now that you have your t, this is your t, you can find Vy at the final point. So when you're doing this calculation, you know Voy, you know the acceleration of y, and you know delta t. So Voy, you can solve for that. Acceleration, you plug that in. T, you plug that in, and you get Vy. Now, it's not asking for the Vy final. It's asking for V final. We know Vx final because it's the same thing as the VO that we already solved for. So this is where we can find the V final. So that's, yeah, it's pretty much the same thing. So I plug in the 0x that we solved for, because it's the same thing as Vx, and I plug in the V final y that we just solved for, and I calculate the magnitude of V final using the x and y components. So technically this would be, if I just wanted to be more clear, I could rewrite it like that. So the V final is equal to 8.044, and you can round that to 8. So the option that you would select for that problem is 8. Okay. Yeah, it's 8. Okay. So minimizing all of that. Okay. So problem number 7 asks, for projectile motion, a pilot drops a package from a plane flying horizontally at a constant speed, neglecting air resistance. When the package hits the ground, the horizontal location of the plane will? The answer is will be directly over the package, because the horizontal velocity will be the same throughout the entire time that the package is falling. It's not going to change. What will change is the vertical component of velocity, because we know that acceleration of y is gravity, and there is no acceleration of x during like horizontal situations like this. So the package is always going to be directly beneath the plane, and the ball or the package or whatever, the only way that it's going to change is it's going to be falling the entire time. So AY exists, but AX is 0. Okay, so for this one, for uniform circular motion, the maximum acceleration a pilot can stand without blacking out is about 7g. In an endurance test, in an endurance test for a jet plane's pilot, what is the maximum speed he can tolerate if he is spun in a horizontal circle of diameter 85 meters? So this is also pretty simple. What might confuse somebody is this little part, 7g. G is not grams, G is gravity. And G's are used in physics as a constant to more easily convey acceleration that somebody is experiencing. Like if you're in a plane, you're like, oh, you're experiencing 5 Gs. Or if you're in a roller coaster, you're experiencing 3 Gs or something. You know what I mean? So 7G is the same thing as 7 times gravity, which would be 68.6 meters per second squared. And it gives you the diameter. The equation that we're going to use is the acceleration of in a circle, like the circular acceleration, is equal to velocity squared over r. We're not given r, we're given diameter. Diameter is like the full length of a circle, and the radius is just 1/2 of the diameter. So we divide 85 by 2 to get the radius. So we plug in, we know the acceleration, we know the radius, we solve for v. V is equal to 54 meters per second squared, and that's the answer. For question 9, projectile motion. A rock is thrown from the upper edge of a tall cliff at some angle above the horizontal. It reaches its highest point and starts falling down. Which of the following statements about the rock's motion are true just before it hits the ground? So basically, you're doing a projectile motion problem. So this is the highest point of the rock, and then it starts falling down. We know that the horizontal velocity component is not 0. There's a horizontal velocity. It's just not changing. The velocity is vertical, not entirely true. There is horizontal velocity. So these two are not true. Its vertical velocity component is the same as it was as it just launched. That's not true because it has acceleration of gravity. So it is going to change at a rate of 9.81. So it's not the same. Its speed is the same as it was just launched. That's not true. VO is not the same thing as VF. However, its horizontal velocity component is the same as it was just launched is true. Vx final or whatever of any point is always going to be Vox, because acceleration of like a parabolic projectile motion problem is always 0. So this is going to be constant no matter what. So this is true. For question 10, uniform circular motion. You are driving at 30 meters per second on a freeway curve of radius 25 meters. What is the magnitude of your acceleration? This one, you literally just plug in stuff. We know that the acceleration of circular motion is velocity over radius. And you're given a value for velocity, you're given a value for radius, just plug them in. Okay, uniform circular motion. An object moves in a circular path at a constant speed. Compare the direction of the object's velocity and acceleration vectors. The only right answer is that the vectors are perpendicular to each other. In circular motion, the vector velocity is always perpendicular to the vector of acceleration. And this is explanatory of the other problem that we recently solved. This one is a little weird. This one is asking, shown below are the velocity and acceleration vectors for an object in several different kinds of motion. In which case is the object slowing down and turning to its right? So this is sort of a process of elimination question, actually. These arrows are a little hard to read if you don't know what you're looking for. So let's do process of elimination. So we know that the velocity is slowing down because the object is slowing down. So velocity cannot be going up, and velocity cannot be going straight to the left-hand side, because this is indicative of it being constant towards the left-hand side, and that's not true. The velocity is going down, and it is experiencing, I believe, an increase in acceleration in the left-hand direction, though I'm not entirely certain how to explain the difference between this option and this option. The way that I've logicked it in my head is if you're in a car and you are turning to the right and slowing down as you turn to the right, the acceleration within your car that continues as you are moving is going to continue on the opposite of where you're turning. So the acceleration is going to be leaning towards the left-hand side, which explains why this option of the last option here, which explains why this option is true. And I believe that's it. That's all of the problems of quiz 3. I hope this helped. If you have any questions, let me know, or message the professor or something. If you know the correct answer for question 13 and know the correct explanation for it, feel free to share that. But this is the way that I've managed to explain it based on what I've read in the textbook. So I'm apologizing if that's in any way incorrect. I don't want to give you incorrect information, but this is how I've thought of it in my head. Thanks.